Let's recall the stability of what carbocations sort of look like. First, we have a benzylic carbocation, then an allylic. Then it depends on sort of how many bonds are to that particular carbon. So if there's a positive charge on the central carbon right there, that would be a tertiary carbon. This would be secondary, primary. In a whole separate category by itself are the ones that are absolutely horrible at having a positive charge, and that would be an sp2 carbon. So an sp2 carbon with a positive charge, generally we don't really acknowledge that it exists so much. Now the reason why these charges are the most stable is because there's multiple resonance structures of these compounds, which we sort of talked about before. pKa is also going to be affected by this delocalization and resonance. So as if you recall, the strongest acid is going to have the most stable conjugate base. So whenever you're looking at, okay, well, which one of these compounds is the most acidic? Really, you're not comparing the acids. You're comparing what the bases look like. And the one that's actually the most stable is the one that's going to exist the longest. So let's think about this in terms of you wearing a coat when it's 90 degrees outside. For all of us who live sort of northern of maybe the Florida-Georgia border, we might get a little bit warm if we are in 90-degree weather, blazing sun, and have a big, huge, thick jacket on. That's kind of like having extra hydrogen. Well, in this case, this wouldn't really be extra hydrogen, but you know, hydrogen that are there needlessly. By removing your coat, you're actually more stable. So that means that you will actually exist like that more often, versus somebody who's in Alaska in the winter taking off their coat. They would pretty much be not very stable by removing their coat. So think of it that way if it helps you. So let me see. I'm going to look at, instead, if I removed one of the hydrogens right here, and we will talk about these types of molecules later in the semester. We've actually got a negative charge here. Now remember, one of these hydrogens still exists, so we don't have a 2 minus, but we do have one negative charge there. This guy can be stabilized through resonance because we could have electrons here go up, and that would take us to that. And actually we could even move this. No, we can't. Sorry. Just take that back. And now we can move these guys back down, which would put you right back here. Sorry. The other way to write that is that we could instead end up with a double bond on that guy, but move the electrons over here. So that negative charge is basically dispersed amongst the 2 oxygens as well as the carbon that's in the center. If you were comparing this molecule to this molecule, and we were to remove that hydrogen, I would have a negative charge right here. And I think you probably already see where I'm going here. There's only one possibility of resonance structures. Right there. Therefore, if you were to compare the acidity of this hydrogen and this hydrogen would be more acidic because of the fact that there's more resonance structures to help stabilize that molecule. Okay? So we've got 3 here versus 2 here. You can also apply that to heteroatom systems, similar types of formats here. If we were to look at, my cat must have knocked over my daughter's ring-a-ding thing. Okay, we've got a negative charge here on the phenol, which would be phenolate. And what we can do in this case is that we can start drawing different resonance structures. So I can move the electrons down here and then to a carbon. Since I haven't done this for you before, I'm going to continue this process. Okay. These electrons can go to that bond, and this bond can go to that carbon. I should draw these as equilibrium. And that's actually taken off an H+. So that's where these electrons go. Those electrons go right here. And those electrons stay there. Not changing a charge, just drawing resonance structures. These guys go here, and this can come up here. And I know that this looks just like this guy in reverse, but because it's a different atom, it actually really does exist that way. Okay, and if I were to draw another resonance structure, it's really the same thing as we started with. So that can go up there, and so that's going to give us back to here. Okay. If we look at instead the cyclohexanol, by removing an H+, that's it. There's no other place for this guy to go. There's nothing to help stabilize that negative charge. And so really, this is kind of like a community sharing a responsibility to hold a baby. And here we actually just have, okay, well, there's only one little lonesome atom there to hold that same responsibility. And that's harder than if you have more things to help share that responsibility, whatever it may be. Okay, so when you're looking at acidity, when you're looking at stability of different carbocations, carbanions, there's a general rule, and that is this type of format. There's exceptions, don't get me wrong, there's plenty of exceptions, but what we're looking at comparing when we're looking at acidity is the two comparing the two molecules that you're looking at. And that means the rules can change sometimes. So you just have to sort of look at that and think about what the reality is and go from there. Okay, on to the next video.